I guess another tool for representing the relationships between different outcomes is to use what we call Venn diagrams. Okay, so a Venn diagrams is really a way in which we can represent a set of numbers. All right, so we've got a few key terms here. All right, so the union of any two sets, okay, is what's we sort of add them together. Okay, and often we talk about A union B as being A or B. The intersection is what's common to both. Okay, so it's got to be in both, and we talk about A intersection or A and B. The complement of A, we've spoken about a complement already. And the complement is what's not in A. So we call it not in A. All right, so if I use these diagrams here, so maybe the blue highlighted first, A union B has got to be in A or in B, which is inside these circles. So that's my A or B section. Okay. The intersection is A and B. What's in both of them? So the area that's just in both is that bit there. Yeah. And then finally, the complement is everything that's not in A. Well, everything that's not in A is everything around this circle. So everything around the circle, try and keep the lines inside the lines. So that's my complement A dashed. Yeah. All right. So let's have a look at this example. So we've got 50 teenagers. They're asked what they did on weekends. A total of 35 said they went to the football. So we'll call A the football, and there's 35. So total of 35 said they went to the football matches, the movies, or both. Of the 22 who went to football matches, 12 said they also went to the movies. So there's 35 of the 50 people either went to the movies, the football, or both. So what does that mean first up? That means straight away that 15 people did nothing. Yeah? So everything outside the circles means they didn't do football or the movies. Now, of the 22 who went to the football, so that 35 there is wrong, isn't it? Let's get rid of that. So let's call that football, and we'll call that movies. So it says, of the 22 who went to the football, 12 said they also went to the movies. So 12 did both. 12 did both, and 22 apparently went to the football. So that means 10 people just went to the football on its own. Yeah. And if 22 went to the football, that means there's another 13 people that must have gone to the movies on its own. All right, so if we check that, we've got in blue, we've got 22 went to the football. We can say in red, 25 went to the movies. And I might just call it green. 12 did both. And obviously our 15 did none. All right, so what does that mean? So there's our information on the Venn diagram. How many teenagers went to movies but not the football? Well, you can see there that's at 13. How many did not go to either of these events? Well, we've discussed that. There's the 15 people that didn't do either. Okay. So we can extend this Venn diagram to come up with a bit of a rule for us. Okay. So what we're saying that if I want to know the number of people that did both, well, if I just add up all the people in that green circle and then add all the people that were in the red, you can see that hopefully, that's all the people in the red, there's all the people in the green. These people here we count twice if we do that, which is why we subtract them off. All right, and that leads us to what we call our addition law, or our addition law of probability. Okay, and that applies to any sort of probability. So the probability of A union B is everything that's in A plus everything that's in B minus whatever's in both, because you don't want to add it twice. All right. Another way representation is what we call our Carnot map, or a probability table. And these are fantastic to represent the sections of our Venn diagram. So my Carnot, if I want to match them off, so we know that the intersection, if you like, is that section there, which is this value, A intersection B. Yeah. Now what's this section here? That says everything that's in A, but not in B. So it's got to be in A, but not in B, which everything that's in A is here, but I can't include that little red section because that's in B. So we want everything in A that's not in B. So that's that section there. What about everything that's not in A, but it is in B? So that's everything that's in B. So everything in this circle is in B, but it's got to be not in A. That's that section. And then finally, everything that's not in A and not in B, well, which means it's not in either one of them. So I'll try and do quickly without making too much. So this section outside the circles, is that, let's try and so that's my blue section. So my Carnot table just highlights the different sections of my probability table, or my Venn diagram. And if we add up these sections, so that's column B, and that column adds up to the probability of B, that row adds up to the probability of A, yeah? Which means the row next to it, that adds up to everything that's not in A, in the same way that this column adds up to everything that's not in B, all right? And then if we add them all together, we should always get a probability of 1. All right, so let's have a look. I might use that. If A events A given as that, find. All right, so what we do first of all, let's call that A, which means that's A dashed, and we'll call that B, which means that's B dashed. And we're told that the probability of A is 0.7, which is there, yeah? Well, let's fill in that straight away. If the probability of A is 0.7, let's fill in the other ones. A intersection B is 0.4. A dashed intersection B is 0.2. So what we can do now is just add our rows and columns and subtract values. So 0.4 plus 0.2 is 0.6, which means if the probability of Z is 0.6, that means the probability of not B is 0.4. And if that's 0.7, that has to add to 0.3, because they all have to add to 1. 0.4 plus something is 0.7, so that's 0.3. 0.2 plus something is 0.3, so that's 0.1. And if I check here, 0.3 plus 0.1 is 0.4. So that's everything in my table. So now I can just use my table to answer all the questions. A intersection B dash, A intersection B dash is equal to 0.3. The probability of B, 0.6. A dash intersection B dash is equal to 0.1. And A union B, well, my rule is that's the probability of A plus the probability of B minus probability of A intersection B, which is probability of A, 0.7, plus the probability of B, which is 0.6, minus A intersection B, which is 0.4. So the union is equal to 1.3 minus 0.4, 0.9. Okay, so really as a guide, whenever we see the presence of, in particular, the complements, so A dash, B dash, if we see them floating around, normally that's a good indicator that we might need to use a Carnow table or a Carnow map probability table. All right, what's 14? Records indicate 60% of secondary students participate in sport. 50% of secondary students regularly read books for leisure. They also show 20% of students who participate in sport also read books for leisure. Use this information to come up with does not, so that's sort of like a R dash, S dash. So let's go with sport, not sport, reading, not reading. And so what have we got? 60% of students participate in sport. So we're going to call that 0.6. 50% of students read books for leisure. So they do read, we'll call that 0.5. And 20% of students do both. So they read and read books for leisure and also do sport. So then now we can fill in all our other values. 0.2 plus 0.3 is 0.5. 0.2 plus 0.4 is 0.6. 0.5 plus 0.5 is 1. 0.6 plus 0.4 is 1. So that must be 0.1 there to satisfy both of them. So students find the probability that a person selected does not read books for leisure. So that's R dashed, 0.5, that one there. Do not read books for leisure and do not participate in sport. So they don't do either one, which is this one here. So that's the probability of R dashed intersection S dashed, which is a 0.1. All right. A couple of definitions. One, mutually exclusive just means that our two events have nothing in common. All right. So in other words, it's impossible to have both of these things occur at the same time. So the example they've got here, rolling an even number and rolling an odd number. Well, you can't do both. If you roll a dice, it's either even or odd, which is why the two sets, okay, are separate. So mutually exclusive is another way of saying there's zero intersection. And if there's zero intersection, my addition rule simply becomes that. Okay, so that's really just a definition to know.